Hello, this is Mrs. Grosch, and the title for today's lecture is Star Power. It's all about stars. You already know a little bit about one star, which is the sun. Like the sun, all stars are huge balls of gas, and they produce energy through nuclear fusion. That energy allows them to be seen because they produce light along with other kinds of energy. Stars are usually found in groups called galaxies. You might wonder how many stars there are in the universe. Well, it's really hard to count them because the numbers are just enormous. What you see in this picture are actually many galaxies, and that's just a picture of a very small part of the night sky. Scientists estimate that most galaxies have thousands of millions of stars in them, and that there's thousands of millions of galaxies in the universe. So the numbers are really amazing. Many stars are much bigger than the sun, but of course the sun looks a lot bigger to us, and that's because of how far away some of those stars are. So let's talk about ways that we can measure distances between the stars. First, let's talk about a unit that's used most when we're measuring distances between planets in the solar system. That unit is called an astronomical unit, and it's based on the distance between the Sun and the Earth. So one astronomical unit is about 93 million miles. Even though that seems like a very large distance, it just doesn't cut it when we start looking at the distances from one star to the next. So instead, we use a unit called a light year. A light year is the distance that light would travel in 1 year, and because light goes so fast, it could go, for example, from the Earth to the Moon in just a little bit more than a second. But to get from the Earth to our nearest star, not counting the Sun, it would take over 4 years. So a light year is an incredibly huge distance. You can see the number there. You shouldn't try to memorize it, but that's how many miles approximately a light year is. And many stars are multiple light years away from us. Stars have what we call a life cycle. Now, we should be clear, we do not consider stars to be living, but they do form and they change over long periods of time, and eventually they run out of fuel, and you could say that they die. So stars are considered to have what we could call a life cycle, and there's really two different pathways that stars could take. You can see them there. Some stars are on the small side, and so they follow one pattern, and stars that are much larger follow a different pattern. We're going to learn about both of them in this lecture. All stars form in a cloud called a nebula. Nebulas are very big. They're also very beautiful. You can find pictures of them that have been taken with telescopes. And they're really huge clouds of dust and gas. Over time, those particles of dust and those gases begin to pull closer together just because of gravity, because everything has a gravitational pull on everything else. So when they get close enough, they begin to form a star. The beginning stages of star formation is what we call a protostar. And what happens in a protostar is that the atoms of hydrogen that are in these big gas clouds that we call nebula, when they pull together because of gravity, eventually they'll start to collide with enough force that will cause them to fuse. And they'll change from being hydrogen to being helium. This is called nuclear fusion. And when nuclear fusion begins, we have the start of what will be a star. But the beginning stages are called a protostar. Depending on how big the protostar is, that will determine what happens next. A smaller protostar will make what we call a main sequence star, which is the most common kind of star. But if the protostar that forms is very large, it will make a way bigger star that we call a massive star. Most stars in the sky actually are considered to be main sequence stars, and scientists who study stars know that they can understand some things about those stars based on what they can observe. For example, we can determine the temperature of a star based on its color. Now, stars are classified by their temperature and their brightness, and we give them letters. So there's O stars, B stars, A, F, G, K, and M stars. In that classification system, O stars are considered the biggest. They're also the hottest and the brightest. And then M stars are the smallest and the coolest and the dimmest. But remember, these are still stars. They're still undergoing nuclear fusion. So even a cool star is pretty darned hot. Those main sequence stars do follow a predictable pattern of how long they are stable and remain pretty consistent and when they start to change. The picture you see here is actually the life cycle of the sun, and so it shows the age of the sun now and about how long it will continue to be stable. But the sun is just one example of a main sequence star. So main sequence stars generally follow the pattern that you see there. All main sequence stars follow this pattern. The main difference is how long it takes for them to go from being stable to being unstable and then eventually running out of fuel. Larger stars that are hotter tend to go through this cycle in a faster period of time, a shorter period of time, and stars that are smaller tend to be more stable for a longer period of time. Now, our sun is a yellow star, and it's a G-type star. So it's pretty stable, it's not terribly big, and it will take about 10 billion years for it to run through the time that it is stable. Right now, scientists estimate that it's about 4.6 billion years old, so we're still good for almost 5 billion more years. During the billions of years that a main sequence star is stable, what's happening is the hydrogen, which is the main ingredient of that star, is fusing to make helium. Well, over time, that hydrogen is going to get used up, but now the helium atoms will start to fuse together to make larger atoms. Carbon will begin to form, and then oxygen. As the helium atoms get used up and carbon forms, well, the larger the atoms are that are forming, the less stable that star is. One thing that begins to happen is the outer layers of the star begin to expand. They move away from the core. As they move away, they actually cool off because the core is what produces its heat. So the large red giant star that begins to form, it's bigger. It certainly is hot, but it's actually not as hot as it used to be, and its color will change to red. A red star is not as hot as a yellow star. This will happen with the sun, as it happens with all stars that are in the main sequence when they begin to use up their hydrogen. As the red giant continues to expand, eventually its outer layers are going to be so far away from the core that the core just can't hold on to them anymore. Its pull of gravity isn't strong enough. When that happens, those outer layers are going to puff off, and they form a circular appearing object that is called a planetary nebula. It doesn't form a planet, but it does have that round shape like a planet has. So it's called a planetary nebula, and those outer layers really do not retain heat anymore. Eventually, they may actually be recycled into new star material in the future. Once the outer layers puff off and drift away, the core of that star remains. Now, there's really no fuel left for it to continue nuclear fusion, but it's still very, very hot because of all the nuclear fusion that was taking place. So they glow very bright, very hot, but they're very tiny. They're only maybe about the size of Earth. At this point, we call the star a white dwarf. Because there's no nuclear fusion taking place on a white dwarf, it can't stay hot forever. Eventually, it will cool off and become a black dwarf. A black dwarf just looks like a little planet. It's not hot, it doesn't glow, and it will just remain that way, well, I guess forever. That's what will happen to our sun eventually. But remember, not for at least 5 billion more years, so I think we're okay for a while. If the star is very, very large, what we might call a massive star, it goes through some changes as it begins to use up its fuel, but it doesn't form a red giant. Instead, it forms a red supergiant star. This is a star that is enormous. Red supergiants are very unstable because their hydrogen atoms are forming helium, but then their helium is forming carbon, and the carbon is forming nitrogen and oxygen, and as those bigger and bigger and bigger elements are forming, more and more energy is being produced. When it gets to the point of producing iron, that's a problem, because at that point that star is in trouble. It has absorbed so much energy that that star just cannot stay together anymore, and it blows itself apart. When a giant star blows itself apart, we have what we call a supernova. Supernovas are incredibly hot, billions of degrees, and we could even see a supernova without a telescope if one happened that was close enough to Earth for us to notice it. It might be visible for days or even weeks, but eventually that supernova would change as well. Now, we are talking about very, very large stars here, but even very big stars, some are larger than others. So the size of that massive star is going to determine what happens to it after the supernova. If it's on the small side, which means up to maybe 4 times the mass of our sun, those stars will create something called neutron stars after they supernova. Neutron stars are very, very small. This is a picture of a neutron star compared to the size of a white dwarf or the size of Earth. So you can see it's incredibly tiny, but it has huge amounts of matter in it, so it's very, very dense. And neutron stars are interesting because they give off radio waves, which allows scientists to study them. Now that would be the fate of a big star that isn't the biggest kind of star possible. For those sorts of stars, after they supernova, they are just so unstable that they actually collapse in on themselves. And this creates something called a black hole. Black holes have so much matter squeezed into a tiny area that they have huge pulls of gravity. The pull of gravity in a black hole is so great that even energy can't escape, which is why we consider them to look black. It's really hard to imagine all of these things happening when you look up in the sky, because we're just not able to see a lot of this stuff, not without good telescopes. But the better our technology gets, the more we learn, and the more we realize that we still have to learn about stars. They are amazing. I hope you enjoyed this lecture. Thanks for listening. I'll see you in class tomorrow.